Hi everybody. So before we get started on this subject, I just want to bring this back. On the last video, I drew this little diagram and then I built this little circuit to demonstrate the function of this speaker decoupling capacitor or coupling capacitor that works between the output of your amplifier and the speaker. And of course, on an electrolytic capacitor, the negative terminal needs to connect to, wait for it, the negative side. So yeah, I drew this backwards, and I think I even wired it backwards when I did it. So that was my fault. I beg your forgiveness on this. I apologize. I was wrong. I did not delete or take down the video. There was other things in that video as well. I did put a big description of that in the description section, but a lot of folks, I don't think, read the description when they watch a video. I'm guilty of that myself sometimes. So just be aware of that. I apologize and hope it didn't cause too much confusion with any of you all. So that's that. Anyway, let's move on. So if you remember, you may have seen, well, let me get it, hold on. You may have seen in the past that I've used this LCR meter here. And one problem when I purchased it was it came with the batteries in it. And I thought that was kind of strange. Normally you don't see these come with the batteries in it. And I think this was an eBay purchase. It was supposed to be new. The box was open when I got it. I probably should have returned it. When I opened it up, the batteries were all corroded. The battery case inside here was all corroded. The board was corroded. I cleaned it up really well and put new batteries in it, and it worked. But over the last year or so, it has become increasingly more unreliable, to the point now you can't calibrate the probes, and it will not hold a reading when it reads. The display jumps all over the place. So this doesn't work anymore. Hindsight is 20/20. I should have immediately returned this. But, well, you live and learn. I got it very inexpensively. These probably sell in the maybe $150 to $200 range for the good, for a brand new one. And this one was a lot less than that, if I recall correctly. So you get what you pay for. Anyway, I used that as an opportunity. I had a viewer bring this particular model. This is the XJW01 LCR meter. And you can find these on eBay, and they run anywhere from maybe $55 US up into maybe $75, depending on what you get. You can get them with or without the probes, and you can get them with or without, I think, with the power supply. And some of them even come with a little battery clip that you can run it from batteries as well. So I'm going to do a review of this. I did go ahead and purchase one, and I thought that would be an opportunity to get a replacement. I really didn't want to buy a really expensive LCR meter at this point in time, so I thought I would give this a shot. So if that sounds interesting to you, stay tuned. So when you purchase one of these, they come, depending on the price, you can get them with or without the probes. And they come with this little stand, which some people probably won't like, but I actually really like it. And it can sit up on there. You get the test unit itself. You get a little wall wart. And then some of the other ones will come with a little battery pack that uses AA batteries with a little barrel connector, so you could run it from batteries instead of from the plug. And then it comes with this strange little bag of parts and absolutely no instructions whatsoever. So the first thing is the mystery of the parts. What are these? And I'll go over this with you. You'll notice that you get a switch, and all this is a spare replacement switch for these. So there's 8 of these little button switches, and if one of them goes bad, they give you a spare. They give you 6 diodes, I think, or 8 diodes, And these are the little diodes that are at the inputs of, mounted on the circuit board of the inputs here for the probes. So I guess if you connect like a charged capacitor or something, it'll take these diodes out rather than damage the unit, and they actually give you some spares. So those are good. So you want to hang on to your spare parts. That's what that is. Now these resistors you would think are spares as well, but they are not. These are actually calibration resistors, and if we're going to calibrate this thing, you will need these. And yeah, you have to really do a lot of searching online. I emailed the seller online, and they were pretty quick to respond with a download link for a owner's manual, which it was in English and it was somewhat understandable, but it still really takes a learning curve to learn how to use this thing. Once you understand how it works, it's pretty simple, but looking at these buttons and what they're called, so you see this one says menu and it has a little, that little asterisk gear looking thing, and then it says RNG and then more little gears. That's for range, I believe. The 0 button and a couple of arrows. Then you have hand or AUT, and that's for actually putting it in manual mode, I believe. You have this clear button, and that's not what that means. It doesn't mean clear. It means this thing will come up in auto mode, just like this one does when you first turn it on, meaning it'll automatically determine or try to determine if you've connected a capacitor, an inductor, or a resistor. What this lets you do is manually toggle through capacitor mode, inductor mode, or resistor mode, and that just lets you scroll from automatic into individual. This lets you scroll through series or parallel testing, and we'll talk about what series and parallel mode is, and it also will let you display ESR. This allows you to, it turns this into like a comparator circuit. So let's say you put a capacitor or an inductor in here and you test it. You can hit the, once you get the results up here of a cap or something, let's say you put a capacitor in, you can hit this quantity button and it'll store the settings or the readings of that capacitor. Then you can take another capacitor, like let's say you're sorting out a whole bunch of 1 microfarad film capacitors. You can take that first reference cap off and then put another 1 microfarad, and it'll show you the percentage of difference between your reference capacitor and all the other ones you're comparing it to. So it's kind of like a capacitor or an inductor matching device, if that makes sense to you. Or let's say you wanted to match a set of resistors, like you had precision resistors and you wanted 2 that were completely identical. You can take one resistor and test it, then hit the quantity button, and then you can go through all your other resistors of the same value and find one that has the closest match. So you can match them. So that's a cool feature. And then you have the frequency button, and most of you that have seen me use this in the past, you can actually determine what test frequency that this thing applies to the device. Now, we'll go over what all that means and why that's important here later. But that's just kind of a rough rundown of what this is. This also uses the Kelvin clip connectors, meaning you have 4 terminals. And if you look at these Kelvin test leads, each test lead has 2 wires. Now, why would you have 2 wires going to the same probe? Well, the reason is when you have Kelvin leads, and that's not my only device that has this. So if you look up here at these 2 multimeters, they both have inputs for Kelvin leads. As a matter of fact, I have Kelvin leads connected to this one right now. And what this does is there's a little current source called the sense lead, and it'll pass a small current between the 2 wires. And it will actually figure out the error resistance of the cables. And it'll subtract that from your reading. So, for instance, when you turn this meter on, if you notice with these Kelvin leads, it reads 0 ohms, exactly 0.000. And if you use a normal set of leads, so let's say these are very high quality, right? These are Probe Master and they're gold tips. And if I hook these up and I touch these together, you can see there is a residual, just a error resistance, and those are from the probes and from the cables. So that's what Kelvin leads are for. Now, yes, you can actually hit the relative button, but setting something to be relative is not the same as removing the error reading of this. So it's different. So anyway, this should be a very accurate little meter if it works, and hopefully it will. Now, all of these LCR meters, whether it be a $70 meter or a $700 meter or a $7,000 meter, they all work on a similar principle. In other words, they will apply a test signal to the device under test, whether it be a capacitor, an inductor, or a resistor. And then it samples the way that that device under test affects that test signal. And it can determine a whole bunch of parameters about that component, about that device, from how it influences that test signal. Now, the main difference is with what frequency that test signal is, how many different frequency points you can test at, and how accurately it can test those changes of that device under test. And that's really the difference between the high dollar items and the cheaper devices like this. Now, this meter, my old meter, it will test at, I'll turn it on here so you can see it. It still turns on, it just, the testing part doesn't work well. If you look at the frequency, comes up with a 1 kilohertz frequency, and if I touch the button, it'll do a 10 kilohertz test, a 100 kilohertz test, a 100 hertz test, which would be similar to a full wave rectified mains in Europe, and a 120 hertz, which would be a 60 hertz full wave rectified in the United States, for instance, North America. So it will test the capacitor under different frequencies. Now, why is that important? Well, there are certain parameters that we're going to check on these devices where increasing the frequency will change those test parameters. So, for instance, low frequency devices like a main power capacitor, like in the main power supply of an amplifier, you would want to check those at either 100 or 120 hertz, because that's the type of signal that's being applied across that capacitor. In other words, the waveform that you're getting on there, the ripple, is going to be either 100 or 120 hertz, and we want to see how that capacitor reacts at that frequency. But when you're working with a high frequency capacitor, like a ceramic cap or a film cap, that's working, like, for instance, in a radio circuit at radio frequencies, you want to be able to apply a radio frequency to see how it affects things. When we look at some of these parameters, I'll explain why that's important at that point in time. But for right now, that's kind of a quick explanation. Now, this one here, as you saw in this meter, it does all those, and it will go up to 100 kilohertz. This one will only go up to 7.8 kilohertz. So my prediction is this is not going to be a really good meter for checking RF capacitors, caps that would be used in a very high frequency radio circuit. But it should be pretty good for checking things like audio frequency. So for checking capacitors, you would use in an amplifier or in a line frequency type power supply, rather than maybe not even a switch mode, but a linear power supply, this should do a very good job. So that's what we're looking at right now. So let's use this and kind of go through how it works a little bit and describe some of the things it tests. Then we'll kind of go through and see if we can do a calibration of it and kind of go through some of the functions and features. Now, one more quick note. When you look at some of the high-end LCR meters, like the ones that are, $700, $800, $1,000 or more, then you can get a lot of money in them. They will have test frequencies of 1 megahertz or above. It's really important when you're testing high-frequency capacitors, especially for radio circuits, like I said. So again, I don't think this will be able to do the test that you would want for that type of a device. So I plug this in, turn it on, it boots up. And you can see it comes up in what's called auto mode. So when it says auto over here, that means that it will try to determine whatever you connect to it, whether it's a capacitor, an inductor, or a resistor. So let's get one of each of those components and see if it can successfully identify the component. Okay, first up we have a resistor, and if I turn this the right way, it's brown, black, and orange. So that means it should be a 10K resistor, brown for 1, black for 0, and the orange for 4 zeros. So 3 zeros, 1 0 0 0 0, 10,000. If we connect it, connect this side here, and let's see, and yep, you could see this changes to R. It's in parallel mode, and it's 9.919K, so it's just under 10K ohms. Now let's compare that to the Keithley, which we know is super accurate. So remember, about 9.92K, so 9,922 ohms. Okay, so now I'm going to connect it to this one, just like so. 9,920 ohms, 21 ohms. So it's dead on. How about that? Really good. And the nice thing is, this thing's just out of the box trying it out. I did not calibrate it or anything, but to my understanding from what I've read, these are supposed to be somewhat calibrated at the factory before you buy them. So that looks pretty good. Next, we're going to throw a capacitor across the bench. Alright, so here we have a 47 microfarad capacitor at 450 volts, electrolytic. And we'll connect it to the device. And you can see it switches to capacitor mode. See, it goes to C, and it's in series. So it's doing a series test. And you can see 45.39 microfarads. It also is telling us that the ESR, or the equivalent series resistance, is 795 milliohms. 4.5 ohms is the internal reference resistance that it's using to test this thing. We'll get into that later. 1 kilohertz is the frequency that we're applying to this capacitor, which really is not the frequency we should be putting on this cap, simply because this is designed for a linear power supply. We should test it at either 100 or 120 hertz. Now, one of the bummers of this is it only has 3 frequencies: 100 hertz, 1 kilohertz, and 7.85 kilohertz, or 7.8 something kilohertz. And so you can test it at 100 hertz, which is European, but you cannot test it at 120. Now, there's not going to be a very big difference, so that's not super important. But there will be a slight difference in the test. So just so you know that, as long as you understand that. This is your Q, or your quality factor, and the higher this number, the better. D is your dissipation factor. Dissipation factor, it's showing the rate at which the capacitor discharges when there is no load applied across it. So this is kind of this is a value, a reference value, to let you know if the capacitor is converting some of its energy into heat and therefore leaking. It's kind of showing the leakage of the capacitor. I don't want to really use that word totally, but that's kind of what the dissipation factor is. ESR and dissipation, all these numbers are intertwined with the internal makings of the capacitor. And then down here, this theta, this is actually showing you the phase angle difference. So what does that mean? Well, if you remember from Eli the Iceman, any of you electronics folks, in a capacitor, the current will always lead the voltage by 90 degrees. If you plot that out on a chart, on a XY axis. And in an inductor, ELI, the voltage will lead the current by 90 degrees. So what this is showing is you should see a 90-degree phase angle between voltage and current. And if you notice what's happening here, it is only showing you a 77-degree. So this has got some pretty nasty phase angle distortion. And that's because of these factors up here. Now if I go and I change the frequency to 100 Hertz, you can see we get very close to 90 degrees now. See, it's 87.9, so it's almost 88 degrees. In an ideal capacitor, this would be 90 degrees. So you can see this is this is a little bit lower end electrolytic. And you can see as you run it at higher frequencies, the phase angle distortion gets worse and worse. So if we go all the way up here, take a look, not anywhere near that. And you can see your quality factors dropped into the dumps. Your dissipation factor is 1.5. So, and you can see right now it is showing your reactance, and this is in series mode. And you can see it even thinks it's a resistor now. See, it's in resistor mode because we're in auto. So the capacitor is so bad that the meter can't even recognize it as a capacitor. So I would have to go over here, and now it's in capacitance mode. And they're now showing you the ESR is not bad, but our phase angle is pretty bad, and our Q and our D are both pretty bad. And the capacitance is still holding. You can see it's a 47 microfarad. It's saying it's 43. But this is an example of what I'm talking about, that the test frequency is very important. And you have to know what the application of the capacitor is that you're testing. We're back in auto mode, and now we're going to try an inductor. And this is 150 microhenry, or 1, 5, and then 1, 0. So it's 150 microfarads, or I'm sorry, microhenries. So hopefully this will see an inductor when you put this on here. So there we go, we're connected. And there you go, 148.7 microhenries, which is good. And that should not change even with frequency. You can see it's still going to read about the same. And if you notice your phase angle, it was minus on the capacitor, and now it's plus on an inductor. You can see at low frequencies, it really doesn't like low frequencies because it's a very low inductance inductor. But if we move this up, you can see now at 7.8 kilohertz, you're almost to plus 90. It's plus 89 point something. So you notice, once again, your test frequency is really important. And this is going to be the Achilles heel of this meter that I'm finding out, is that you just don't have enough range or enough steps in test frequency to really be able to test every single type of device out there, especially reactive devices like capacitors and inductors. So I think that's going to limit what we're going to be able to test with one of these. I'm now back in capacitor mode, and we're going to check this. I always recommend these for audio path, you know, to replace like the electrolytics. Any electrolytic under 4.7 microfarads, I always use these film capacitors, and I like these WIMAs or WIMAs, however you want to pronounce it. This one's a 2.2 microfarad at 100 volts. And this is a stacked film capacitor. So it's not ceramic, it's not a silver mica, but it's a stacked film capacitor. And let's measure what it says. Remember 2.2 microfarads, and you can see 2.148 microfarads. That's good. And we can see the phase angle, even at 7.8 kilohertz now, hardly has changed. It's 89.59 negative. You can see because it's a capacitor. ESR is almost immeasurable. It's tiny. The dissipation factor is super tiny. This is why you use a film capacitor over an electrolytic in this, because if I got an electrolytic, as a matter of fact, let me go get an electrolytic 2.2 microfarad. Okay, here's a Nichicon PW series. This is a really common type of capacitor that people use in the non-audio path section of amplifiers. So for power supplies and things like that. And it would help if I put my microphone on so you could hear me better. I hope you heard me. Hold on. There we go. So like I was saying, this is a Nichicon PW series, very commonly used on amplifiers like in the power supply sections and things, places not in the audio path directly. And it's 2.2 microfarads at 100 volts. So it's the same, exactly the same rating as this capacitor. So let's see what it looks like. So we connect this up. And you can see when we go to 7.8 kilohertz, you can see that first of all our ESR has gone way up. It was like 0.06 something. Now it's 1.8 or 1.9 ohms. You can see that your phase angle, instead of 90 degree, it was 89 point something on that film cap. It's 78.9 now. You can see your dissipation factor and your Q, everything has changed a little bit. So, and that's because you're at 7.8 kilohertz. If we move down to 100 hertz, which would be like a linear power supply, when this thing settles, you can see the ESR is even higher. Dissipation factor goes way down. Your phase angle, though, gets back closer to normal, 88.9 just about, or 88.87. And you can see your quality factor goes up a little bit from what it was. So you can see that these things they are affected by frequency. Now last but not least, this is one that was pulled out of an X-ray machine. And this was out of a high frequency generator. This is a circuit that drives a set of an IGBT inverter circuit at well over 250 kilohertz. And this is an extremely high quality capacitor. And it's also a film capacitor, but it's a special winding that has inverse wound elements in it, so it cancels out the inductive reactance. So these are designed for very high frequency. I'm going to connect this up. And we're at 100 hertz right now. Let it settle a little bit. You can see everything's beautiful on this. Look, the Q, it's maxed out. That's the highest reading this can do, is 999. Your dissipation factor is 0.001. ESR. And you could see your phase angle is almost bang on 90 degrees. Now watch what happens when I change the frequency. There's 1 kilohertz. Notice nothing changes hardly. Everything is super. The dissipation factor gets even better. And if I go to 7.8, look at that. Dead on. So it's almost acts like an ideal capacitor, or as close to it as you can possibly get. And the higher you go in frequency to a certain point, the better. Here's the issue. You really can't test the limits of this capacitor with this device. And this is showing you one of the limitations of this particular device. So if we had 100 kilohertz and a 1 megahertz test frequency, we may be able to see the point at which this starts to have a phase angle change and so forth. But on this little particular device, this low-end one, you're not going to see it. So that gives you an idea. So 3 capacitors that all have the same value, but very different characteristics, huh? Now, as a general rule of thumb, when you're testing big electrolytic capacitors like this or higher, and they're running in a linear power supply that's running at mains frequency, dissipation factor is going to be more important than phase angle change. However, when you look at high frequency capacitors, and I'm not even going to bother, here's a silver mica. Silver mica and ceramic, really this isn't going to give you a good evaluation of it at all. And you can see it's confused somewhat, because these need to be tested at a very high frequency. And as you test these at really high frequency, you're more interested in how the phase angle is affected than the dissipation factor. You're not worried about how well it stores energy and leaks, but you're more interested in how it changes the phase of your current and voltage. You want them to stay within that 90, as close to 90 degrees as possible, because once again, if this is a radio circuit and you're changing the phase angle of your current and voltage from what a capacitive reactance is supposed to be doing, it could affect that RF circuit at very high frequencies. So that's why ceramic capacitors and those types, you're more interested in this, whereas line frequency electrolytics and so forth, you're going to be more interested in the dissipation factor being low. So hope that makes a little bit of sense. So that kind of shows me that this is going to be okay for things that like audio amplifiers, guitar amplifiers, things like that. We can look at like the film capacitors or paper foil capacitors. We can go into comparison mode and we can like compare caps and things for that. but it's really not going to do me any good for radio frequency capacitors like the ceramics and the very low picofarad value caps. Even though this can measure into the picofarads, it's not going to really tell us what it's going to do in a high frequency environment. So another thing about this phase angle, some LCR meters do not show you the phase angle, but rather they'll show you what's called the loss tangent. And what all that is a fancy word that means it'll show you the difference between 90 degrees. So for instance, on a capacitor, it may show you that it's either plus or minus 2 degrees off of 90 degrees. So when you're looking at loss tangent, it's the same thing as phase angle, except it's just showing you the deviation from what an ideal capacitor would be. So for instance, an ideal capacitor would have negative 90. And if you notice, when we connected this capacitor here, this electrolytic, and I'll take it down to 100 hertz. So your phase angle, wait till it stops here, is minus 87.88. So that means you're going to be off by a total of, well, let's call this 88, of 2 degrees. So or in this case, it would be 2.1 or 2.12 degrees, if that makes sense. So instead of this saying 87.88, it would say 2.12. And all that is your loss tangent, which is how much deviation from that 90 degrees you are. So I hope that makes sense. I mean, if you're not fully understanding what I'm talking about, you might want to go online and look up, for instance, capacitive and inductive reactance. Just Google search that. And also a fun thing to look up would be ELICE, E-L-I-I-C-E. And I'm sure that'll pop up some articles on how reactance works in an inductor and in a capacitor. Now, dissipation factor is the ratio of your ESR to your capacitive reactance. So to display capacitive reactance on this, we have to go through and put this into resistor mode. So if we scroll, there's inductor, there's resistor, and you can see it's showing that our reactance is 34.53 ohms. And we're not worried about the negative or the positive, that doesn't matter. So if I write that down, 34.53, and then I go back to capacitance and I look at my ESR is 1.28. So take our ESR, 1.28 divided by 34.53 equals 0.37. And if you look what it says. How about that? Sometimes the math actually works out. So that's what your dissipation factor is. And what this is really showing you once again is it's a number that describes how fast the capacitor is converting stored energy into heat. In other words, it's dissipating it as heat, quote unquote leakage. So it's the capacitor is leaking. And that's the dissipation factor. Obviously, the lower that is, the better. So for any of you that want to actually purchase one of these, we'll go over some maintenance items on it. The first thing is calibrating the probes, which is easy. So we're going to take these probes and we're going to separate them, leave them plugged in, and we're going to hit the 0 button, and it says open 0, and it's calibrating the 1 kilohertz, then the 7 kilohertz, and then the 100 hertz. So it's basically nulling out the signal with nothing, with the probes open. And any kind of noise or any kind of garbage that's on these probes, it's basically canceling that out. Then we can short them like that, and we can hit the button again. And see, it knows that it's shorted. Now it's nulling out the probes while they're shorted. So what this is going to do is this is going to essentially take the influence of your probes and the probe leads and the connectors and all that out of the picture. And the reason this was so accurate compared to my other meter was because I had already done this before the video. So it's as simple as that. Now, normally that should be all you have to do. And because these are supposed to come from the factory, with parentheses around should be, they should be factory calibrated. If not, that is why they give you these resistors. And there's actually 19 steps you have to go through. It's quite involved to actually calibrate this. So maybe we will attempt that, and I can kind of show you how to do that if you need to. Okay, the last thing we're going to do in this video is we're going to calibrate this unit. And there's a couple notes you're going to need. Number one, these resistors, you can measure them, but the more accurate you measure the actual resistance of them, the better. They're supposed to be 0.1% tolerance resistors, but they're not always perfect. So I went on my Keithley using the Kelvin clips, the Kelvin probes, and I actually measured the actual resistance. So for each of these resistors, I marked the actual resistance that they measured, and then I just took some some sticky tack here, blue tack, whatever you want to call it, and I just stuck the resistors in there so to make it convenient. Now for some reason, there is one resistor in one of the steps that they don't include, and it is a 25 ohm resistor. So you need a 25 ohm resistor to do the test. And if you don't have it, it says you can skip right through that particular step. But what I'm using is just one of my little resistor decade boxes, and I have a jumper configured for 25 ohms, and it's really close to 25. It's like 25.1 or 25.2, so no worries there. So to get into the calibration menu, this thing's a little bit goofy, but you get used to it. You hold the menu key down for 3 seconds, and it'll give you that little display there. To begin there are 19 calibration parameters, and I'll try to walk you through them and show you how they work. Now this has been perfectly calibrated, so I'm not going to make it or save any of my changes. I'm just going to walk you through the process. So once you hold this menu down for 3 seconds, you get this display. You hit the range button, the RNG, and that starts with step 1. Now here's the thing. To go forward in the steps, you're going to hit the frequency button. To go back 1 step, you hit the quantity button. To change your values up and down, you're going to use these 2 buttons here, the CLR and the ESR buttons. And then when we're finally done with the whole thing, we're going to hit this hand AUT button, which is hand and automatic, which is going to save all. There's no indication when you push the button. It doesn't beep, nothing happens, but it does save your settings. Now, the one thing you don't want to push is the 0 button. If you hit the 0 button, it will delete this setting, and it will fill it with a default setting. If you go through and set them all to default, it will be a little bit accurate, but it won't be perfectly accurate. So just remember, if you push this 0, you're filling it with default settings, factory defaults. So the first thing you want to look at is this is indicating your step, and this is indicating what resistance it's looking for right now. So when you see 0, 0, 0, that means it wants you to short the probes together. And by the way, before you do this for real, you want to turn the machine on and you want to do that 0, and you want to calibrate the open probes and then calibrate shorted probes, just like I showed you earlier in the video. So do that first, then go into this menu. So we're going to short our probes together. And the idea is you want to set this for 0. You can see it's bouncing between 1 and 0. And the DAC number, or the data number right now is 82. You can see if I move that number, it throws that off. You see that? And the idea is we're going to adjust this till there's 0 ohms. Okay? Or as close to it as possible. If I go this way, it'll go up. See, so 82 is where it wants to be. When I'm done with that, I go to the next step, and it's going to do the same thing. Okay? And you're going to set it for 0. And there's your data. Because see, it's still asking for shorted probes. The third step, and this is just stepping you through for the different frequency, okay, for 100 hertz, or 100 hertz, 1 kilohertz, and 7.8 kilohertz. Okay, now you see it changes to 40, so we want to get our 40 ohm resistor. So if we look up here, you can see my 40 ohm resistor tested very close to 40 ohms. So almost dead on 40 ohms. So I'm going to pull that resistor. I'm going to connect it into the probes, like that. And you want to adjust it till it says 40 ohms. Now if that wasn't 40 ohms, I'd go up and down with my data number until it calibrates into 40. Go to the next one. This is your phase angle. So now with that 40 ohm resistive load, you're adjusting phase angle to be 0 because this is a non-reactive load. It's a resistive load. So it should be 0 degrees phase angle. So that's what we're going to do. And we just move this number up and down until it's as close to 0 as possible. And there is background noise on this. So you see it'll bounce around. So you get it as close to 0 as you can. This is where the one step where it asks for the 25 ohm resistor. And what they're saying is if you don't have a 25 ohm resistor, leave that parameter at 0 or at whatever it's at. But in my case, I have a 25 ohm, my little decade box. And you can see it's 25.2, like I told you, was what it measures, roughly 25.25 or something like that. And you can see it's right on. So we don't have to adjust that. And you can just see I have it connected here. And I used the Keithley to measure this, to make sure that I had the exact resistance. Move on to the next. And now it wants the 1K resistor. So now we're going to pull the 1K. And if you notice, the 1K resistor is reading 0.99755K, so it's not right on 1K. So we're going to put this in, and we want it to say 0.9975. And you can see it's right there, because I calibrated this earlier. Again, we want our phase angle set to be 0, with the 1K resistor in. Now we want to put the 10K in. All right, so the 10K is 9.9891K. If you don't have an accurate ohm meter, don't sweat it too much. Just use the value. You can see how close it is to exactly 100K or 10K or 9K or whatever. But if you want to get it splitting hairs, you can do this. So 9.989, and you can see that's how I have it set. Once again, this is your capacitive reactance, and it should say as close to 0 picofarads as possible. Because again, all of these tests are done with resistive loads. Next, This is 0.1 mega ohm, so don't get confused by that. That would be the same as 100K. And our 100K resistor reads 99.936. So we're going to put that in there, like that. And you can see it's pretty close. Bounces around a little bit. The real high resistance like that, it'll do that. And then we move to our next parameter. Same thing. These are for all the different. And again, we want our capacitance set to 0 as close as possible. Now it wants the 3K resistor. So remember, I would be moving these DAC or these reference numbers up and down if our parameter was off. Okay. So our 3K, and you can look here, our 3K was very accurate, 3.0035K. So 3.004, because it can't go to that last digit. So it's right on. Again, the capacitance. And some of these capacitance points will bounce around a little bit. So like you can see, this is 1 picofarad, a little bit over 1 picofarad, and it's in the negative. And if I go the other direction, see it kind of bounces around and it changes to henries and it goes crazy. So it's right on 0. All right, 9K resistor. Put that in. There we go. And our 9K is 9.0045. And you can see it's right there. 9K, again, we want to set it for 9.0045 roughly. Capacitance, set it to 0. And now we're going to move to our 1K. Sorry, I bumped the camera. So our 1K, we put our 1K resistor in, and we want our phase angle to be 0, because once again, this is a non-reactive load, so you want to set this to as close to 0 with that 1K resistor in there as possible. And you can see it will bounce around, so if I move this number, you can see how it jumps to negative and positive, so it's pretty close. Surprising how accurate you can get this thing. So now we're back to 0, 0 again. And you can see, again, we've just flipped around all the way back to the beginning. It's that simple, okay? I know I went through it pretty fast, but that's really all there is to it. As long as you do this in the order that I just showed you on this video, it's very easy to do. Once you're done, you would hit this hand or auto button, this blue button. You just push it one time. It will store your settings. And when you're done, hold the menu key down. It brings you back to that menu, and then you just turn it off and back on. And you're all calibrated. That's all there is to it. So last but not least, let's check one of these giant capacitors. This is a cap that came, this is the one that came out, I believe, of that SAE amplifier we just did the restoration on. And this is supposed to be, where does it say? 10,400 microfarads. Okay. Minus 10 or plus 75%. And this is a good example here. This one may not read. Now this can go up that high. This meter is capable of going up to, I think, 20,000 microfarads or something like that. Or I think it's 20,000 or 200,000. I can't remember. But you can see it doesn't know what this is. So we're going to hit capacitor mode. And instead of microfarads, it goes to millifarads. So what this is saying is that it's reading 60,000 microfarads at 1 kilohertz. So now we got to change our frequency. These capacitors here do not like high frequency. So if we move it down there, and we can see 100 hertz, and it's reading about 3,200 microfarads instead of 10,000. Not reading too good. And you can see the phase angle is way off. Dissipation factor is really high. The Q is really low, the quality factor. The ESR is good though. So if you put an ESR meter on this thing, it would read like a good capacitor. But in fact, this is not a very good, this cap isn't in really good shape. So here is one that's 10,000 microfarads at 50 volts. Let's connect it and see what it looks like. I just pulled it out of the bin. I don't even know what it's going to look like. There it goes. Okay, there, I was out of range. Now it's good. Sorry about that, guys. So this one is 9,940 microfarads, or 9.9 millifarads. And you can see the phase angle on it is very close to 90. It's much closer than that other one. Dissipation factor is very low. The Q is much higher. You can see we have 18 milliohms for the ESR. So this is a much healthier, much healthier capacitor than this one. So there you go. So that just gives you an idea of how it works. And you'll find that this meter is a little bit finicky with high capacitance caps. You got to really get the probes on there well. You have to toggle the range switch until it gets into a range that it can measure it. But it will measure large filter capacitors. And when it does lock on, it does a really good job. So there it is, the XJW01 LCR meter. Would I recommend it? Well, for 70 bucks or 70, $50 to $70, depending where you find it and what you pay, what you get, the probes or not. Yeah, I probably would, with this caveat. And that is that if you're going to use this LCR meter, it will work very well for things that run at line mains frequency, like linear power supplies, audio amplifiers. I think this will tell you enough about a capacitor or an inductor to give you a good idea of the quality of the component that you're going to use in your amplifier or your stereo. But I would not use this in RF capacitors, anything that's, or really high frequency inductors. Anything that's going to use in an oscillator circuit, high frequency oscillator, this is just not going to be able to give you the information you need. You really need to test those types of devices with a 1 megahertz test frequency, not a 7.8 kilohertz test frequency. So understand its limitations, but for the price, it's wonderful. I like the stand. I like the sturdy metal case it comes in. I don't like the confusing buttons, but once you find your way around them, it's really not that bad. So there you go. Hopefully this was a helpful video to all of you and it'll help you make your decision whether you want one of these or not. I'm going to leave it on my bench and use it, but obviously it'll work really well for the amplifiers and things, but I won't be using it for high frequency stuff. So that's it for this video. I hope you enjoyed it. And as always, I wish you all peace, joy, happiness, and good health in your lives. And we'll see you again real soon. Maybe we'll give this thing a workout on our next project when we do the AM80 radio or tuner, and then we go to build our little amplifier project to go with it, and maybe we can test some capacitors and things with that, who knows. But anyway, until then, stay well and take care. I hope you all have a great afternoon or a great day. Bye-bye.